Good day. This is the third in a series of videos designed to explain how to create predictive models which are simultaneously explicable and precise. The topic of today's video has to do with missing values. So we'll talk about what they are, how people have dealt with them in times past. We'll first get into the mathematics of it because, as we've said all along, mathematics tells you what arithmetic is useful and what arithmetic is superfluous. We'll see how that plays out in practice, and then we'll make some observations about what this means for categorical variables. So here we go. So here's the deal, is that missing data is a perennial problem. This happens all the time, and it's not a question of whether or not a certain data set is clean. It is simply that cleanliness has to do with the degree of the data. There's no clean data set in this world. And so then the question is, well, what do you do about it? And so, as I said, that's a perennial problem. You have to deal with this with any data set that you have. And so what do you do? And so these observations, or rather these suggestions here, come to us from elements of statistical learning. And I'm not picking on those guys. Those guys are great. They've done a lot for data science and statistical learning. I'm simply making the point that it's a very popular text, and these are some of the suggestions they make. But I've seen these other places as well. And so one idea is, well, look, you're just going to discard observations with missing values. But if you have a bunch of variables, the probability that at least one of them is missing in any given case, of course, increases with the number of variables you have. And so that doesn't seem like a particularly robust idea. Another suggestion is, well, just rely on the learning algorithm to deal with the missing values in its training phase. And so what is it? That's just passing the buck. So then you can just go back one step and say to the fellas who derived or programmed the learning algorithm, hey fellas, what'd you do with the missing data? And then another one is, well, you could impute missing values, right? So maybe if you have a missing value for a variable, you take the mean or the median of the places where that variable is populated, and you just use that for the value there. There's all sorts of different things that you could do. But again, just like our question about how do you standardize variables, all of these suggestions really belie the fact that there doesn't appear to be an underlying theory for how to deal with missing data. Is there a canonical method to deal with this? And again, apparently there isn't, since all these suggestions are being given. So to explore what this might look like in practice, let's go to our good friend RStudio to get some intuition about how this could work. So on to RStudio. So here's what we're going to do. We're going to fabricate a data set here. We are going to create a target variable whose coefficients are 1, 2, and 3 and an intercept of 4. And just to make sure that we actually did that, we'll run a GLM on it. Sure enough, 1, 2, 3, 4. Those are our estimates, so good. We're not doing anything too foolish, at least not yet. Now, next, to illustrate missing data, what we're going to do is mark some of these observations as missing, and we're going to mark roughly a third of each of the variables as missing. Now, hopefully your data is a little better than that, but hey, you know how it goes. Now, one of the things that's going to be important as we go through this talk is the idea of in what situation you find yourself. And so here's the deal, is that we have 3 missing variables, and therefore there are 8 situations. In the first case, all of the variables are populated. Yay us. In the second case, well, the first one's missing, but 2 and 3 are there. In the second case, the second one's missing, but 1 and 3 are there. The third case, or rather the fourth case, the third one is missing, but 1 and 2 are there, and so on. Well, what you can do in order to keep track of which situation is in play for any given record is you can think about these indicators, these missing indicators, saying, is the first guy missing? Is the second guy missing? Is the third guy missing? You can take those indicators and multiply them by powers of 2 and add them up. And what will happen is you will get a unique value depending on who's populated and who's not. And so just to give you an example of this, so situation 3, 1 and 2 are missing. Situation 0, all of them are populated because it's false, false, false times powers of 2. Situation 1, first guy is missing, the other 2 are populated, and so on. Here in situation 4, 1 and 2 are populated, 3 is missing, and so on. So you use the indicators of missingness combined with powers of 2 to mark in what situation you find yourself with each record. Now, to illustrate where we're going with some of this, let's create some bogus values for our variables where they're missing. Now, you might say, that's even worse than imputation. And you'd be correct if we were just going to leave it that way, but we're not. Because we're also going to create these indicator functions which tell us precisely when the original variable was missing. And here's the intuition that we are going to expand to the general case. And we're simply going to start with a case. So let's just suppose we have exactly one variable, and we're going to make a model with it. You would say, well, what are you going to do? Well, sometimes it's missing and sometimes it's populated. Okay, so how about this? Where it's populated, we'll build a model, and where it's missing, because we don't have any information at that point, we are simply going to use the sample mean. Does that sound reasonable enough? And so here we build a model. It's called populated coefficients. Why is that? It's like, well, it's because in the data set that we feed into the model, that's precisely where the indicator that it's missing is off. So that is to say that the variable is populated. And so now here we'll build an intercept model, and you can tell it's an intercept model because it's just regressing against 1, regressing against the intercept column. And you can tell that what we've done is we've simply said, here's the data where the indicator's turned on. That is to say, we are just going to take a look at the sample average where the predictor variable is missing. And so now the real question is, okay, all well and good, is there a way to do this simultaneously so that I don't have to create 2 different models? And the answer is yes. What we're going to do is, and this is why we created those bogus values so that they wouldn't get rejected, I mean, among other things, by the GLM function, is we are going to put both the predictor variable and its indicator into the model, and that's the all coefficients model here. And so the idea here is that in sort of at first glance, what you would do is you would build 2 models. You would build one where the variable is populated, and then you would build a second one where the variable is missing and just use a sample value there, or sample average there. But in fact, if you regress against both the variable and its indicator, and then you just put some dummy value in for where the original variable is missing, you will get back the same model. And so what do I mean by the same model? Well, what I mean is take a look at these coefficients coming out of each of the models. And you say, look, in the case where we used all of the data, where it was populated and where it wasn't, look, the coefficient coming out on X is exactly the same. And the intercept is coming out exactly the same. But you'll notice that we do not get the same value here. It's like, okay, well, we got 1.33 and 710. What happens if we add this to this? We get 1.97. Okay, that's not 7.1. Okay, so what's going on here? And the answer is quite simple, which is that, well, look, remember, where the variable was missing, we just used the dummy value of -1. Well, when you multiply -1 times 0.8769, and then you add that to this intercept, and then you add to that the coefficient on the indicator function, you get precisely the sample average where the data was missing in the first place. And so that's the intuition that we're going to try to expand here, is that you have sort of two situations in the case of one variable, where it's populated and where it isn't. Therefore, you want to build a model in each of those cases. And then you think to yourself, oh, wait a minute. If I'm mildly clever, I can figure out a way where I can create both of those models simultaneously. That's the idea. And so with that in mind, let us now go back to the slideshow. Okay, and now let's go through the mathematics of this. So now we're going to sort of think through some of the suggestions about data imputation, right? And so let's think about that suggestion. So with data imputation, they would say, okay, well, in the case that x1 is missing, let's just make x1 let's model x1 using everything else. Again, if you're using the sample mean, that's just simply, using an intercept model to impute values for x1. But this is the more general case, is when x1 is missing, you use everything else. And if x1 is not missing, then you just build your conditional expectation as per usual. But you should notice that when x1 is missing and you use the imputed value, implicitly then what you're doing is you have your conditional expectation, which is built off of x1 through xn, but x1 you're replacing with some function of x2 through xn, and then you also have x2 through xn here. So really that's just a function of x2 through xn in the case when x1 is missing. And so now in practice, when you're talking about n predictor variables, well, what does that mean? That means that there are 2n situations depending on which variables are missing for any given record. And so what does that mean? Well, that means in practice, because there's 2 to the n situations, that means there are 2 to the n different conditional expectations which need to be estimated. So that's a bummer. And so here's how we're going to deal with this problem, is we are going to enlarge the set of real numbers. Now, you might be saying to yourself, what does that even mean, to enlarge the set of real numbers? That seems kind of weird. But my rejoinder is that you actually are already used to doing this. So let me motivate that idea for just a moment here. So realize that when you think about just the counting numbers, 1, 2, 3, 4, 5, and so on, we realized long ago that that was insufficient for our conceptual needs as humans. We kind of needed some other number to demonstrate absence. That would be the real life interpretation of 0. Nothing's there. Something's absent. The mathematical interpretation of 0 is we want to solve the equation 2 plus x equals 2, and you cannot solve that equation with the natural numbers. So you enlarge the natural numbers. You enlarge the natural numbers to include 0. And now with that, we're very pleased with ourselves. But then we realize, we still don't have enough numbers, because now we don't have numbers to indicate not necessarily an absence, but rather a lack of something. And so we should say, there really should be, 3 lawn chairs here, but there aren't. So we're down 3 chairs. Mathematically, what that means is we want to be able to solve equations like this. So now that we've introduced 0 into our counting numbers, we want to be able to solve equations involving it. So here's 2 plus x equals 0. But we can't solve 2 plus x equals 0 with the natural numbers and 0. So we have to enlarge our number set to include negative numbers. So yay us. But wait, negative numbers, that still doesn't help us all the way, because sometimes we want to think about things that are less than 1 but bigger than 0. So I take a pie, I want to be able to divide it into 2 pieces for 2 fellows. Now, I don't have a number to express a whole cut into 2. Arithmetically, or rather mathematically, what that means is I don't have a number to solve this equation here, 2 times x minus 1. I cannot solve this equation with simply the integers, and thus I introduce the rational numbers. But wait, the rational numbers still even aren't big enough, because there are some numbers that I can't express with only rational numbers, and 2 of those examples are the square root of 2 and it's roughly a freshman, sophomore level exercise to prove that the square root of 2 is, in fact, irrational. It cannot be expressed as the ratio of two integers. And in fact, where does this come up? Well, if you have a unit square, right? So if you have a unit square, you know from the Pythagorean theorem that a squared plus b squared equals c squared, where c squared, or c represents the hypotenuse of the unit square, which means that it has length, square root of 2. So you can very easily and naturally produce lengths of irrational length. Similarly with pi. Now the proof that pi, what's amusing here is that the difference between square root of 2 and pi is quite vast when we're talking about the proof that they're irrational. So as I said, square root of 2, that's irrational. That is simply an exercise for sophomores in sophomores in college. It took until about 1768 for Lambert, using continued fractions, to prove that pi was in fact irrational. So we enlarge our numbers yet again, and so going through such exercises, that is how we get up, we build up to the real line. And so all I'm asking the viewer is that we do it again, is that the real numbers now seem insufficient for our purposes, because we need to represent the idea of missing. We need to represent the unknown as such. And so here's what we're going to do. We're going to define the extended real line. So we're going to take the real numbers and we're going to add some other element, perhaps we'll call it z, to it, and we'll call that r bar. And so now what we're going to do is, for an extended real valued random variable, which means it takes real values or it takes the value missing, we're going to define an indicator function. And it turns on when the variable is missing, and it turns off when the variable is populated. And so now what we can do is, if we have some real valued random variable, not extended, but real valued random variable that we are perhaps trying to predict with extended real valued random variables, in the case of two variables, this is what we're going to do. We're going to take the number 1 and we're going to write it in a very odd way. We're going to write it as 1 minus the indicator for x1 times 1 minus the indicator for x2 plus 1 minus the indicator for x1 times the indicator for x2, and then plus the indicator for x1 times 1 minus the indicator for x2, and finally the product of the indicators. Now, why would we do such a thing? And the answer is quite straightforward, which is that what we're trying to do here is we are trying to represent every possibility that can occur when you have two variables on which you're modeling. And so each of these terms here represents what will happen. So this term is turned on if both variables are populated. This term is turned on if only x1 is populated. This term is turned on if only x2 is populated. And this term is turned on if both variables are in fact missing. And so then we write the conditional expectation of y given x1 and x2 in this fashion here. We're just using our good friend the distributive property. And then going, well, yeah, wait a minute, but in this case, in this term here, only x1 is populated. And in this term here, only x2 is populated. And in this term here, neither of them are populated. So really it just looks like this. We have a conditional expectation that relies on both variables where they're populated. One that relies only on x1 where it's populated, one that relies on x2 where it's populated, and finally just your straight expected value on the set where both of them are in fact missing. And so now what you do is you move on to how this looks in practice. And so in practice, here we go. For each of the 2 to the n situations, what we're going to do is we're going to create a model that uses whatever subset of variables is populated. And so we're going to have to create 2 to the n models. And we go, oh gosh, how are we going to do that in some reasonable fashion? That is to say, how can this be done simultaneously? And the answer is, well, here's what we're going to do. For each predictor, you create your indicator function that indicates when it's populated or missing. You impute to it some dummy value, that is to say, you impute to x the predictor variable, some dummy value when it's missing. And I like to choose the minimum -1 because it's by definition not in the data. And then what we're going to do in the case of at least the 2-variable case, we're going to create 4 sets of terms. These are the terms against which we will regress when everything's populated. These are the terms against which we'll regress when x1 is missing, but x2 is populated. These are the terms against which we'll regress when x1 is populated, but x2 is missing. And this is what we're going to regress against when neither of them is populated. All right, so for each predictor then, in the more general case, we're going to create the indicator. We're going to impute the missing values with some dummy value. But then what we're going to do is we are going to create indicators of the form, just a bunch of factors. And what are those factors? Well, they're either the indicator or 1 minus the indicator. So when they're the indicator, that's indicating that the variable is missing. When it's 1 minus the indicator, it's indicating that it is populated. And then we're going to look at all of those products like that, and we're going to multiply the variables which are indicated to be populated, that is to say, this variable is turned on, by the indicator with the indicator. And so what this is going to create is this many terms, 2 to the n times n plus 2 terms. And then once you've created all of those terms, each one representing a different situation, when you regress against all of them, that will be the equivalent of creating the 2 to the n different models. So, again, let's go back to our good friend, RStudio, and see how this looks in practice. So, bringing up RStudio. All right, so here is where we create what I refer to as the full design matrix. And let's get those names. All right, so now let's take a look at what this looks like in practice. So you can see here all of the different possibilities. So here are the columns for when everything's populated. So we've got a column for each of our 3 variables, and then one for our intercept term. When x1 is missing, we're in situation 1, so we don't need x1, we just need x2 and x3. These are the columns for situation 1 for x2 and x3. And here's the intercept for situation 1. In situation 2, x2 is missing, and we just need the columns for x1 and x3, so here they are, and here's the indicator for situation 2, or intercept column for situation 2, and so on. So this now, we've taken our 3 variables. Originally we just had 3 predictor variables, and now what we've done is we have created indicator functions, and then we've created columns corresponding to each of the possibilities for who's missing and where. All right. Include our target in our data set. And then total model. So just to give you an idea here, let's take a look at the formula here. So I've got the target, and now I've got the variables for situation where everything is populated, the variables for the situation when x1 is missing, the variables for the situation when x2 is missing, all the way down to just this guy, which is the situation when everybody's missing. And because we have included an intercept column for each of these, we tell the function, the GLM function, hey, don't throw in an extra intercept column. We've got it handled because we're so clever. So we create that model, and then we create the predictions from that model. And now to prove to you that, in fact, yes, we do, in fact, we have, in fact, simultaneously created all 8 of those models. What you can do is you can do something like this. We are going to simply look at, so the total model here, that's just whatever came out of the predict function. That's all 1,000 predictions. What we're going to do is we are going to look at the predictions, but only for each of the different situations. And we are going to compare that with what comes out of a GLM when you regress against all those guys, where the situation is built precisely on the data for that particular situation, and then look at the fitted values that come out of that. And what do we see when we do this? Well, lo and behold, the difference between what came out of creating all of those models simultaneously versus creating them individually, when you compare the predicted values on the data, they agree to the 13th, 14th decimal place. So I'm okay with that level of precision. Hopefully you are too. So with that in mind, that kind of showed that it works. I want to get back to the slideshow now and show how this works in practice when you are talking about categorical variables. So there's actually a simplification that takes place if you know ahead of time that you're dealing with a categorical variable. And it's exactly what you think it is. So I'm going to go through a bunch of math in these kind of upcoming slides, but just keep the goal in mind that if you have a variable like state or something like that, so in the United States we got 50 states. If it's possible that state is missing sometimes, what that really means is you have 51 states. You've got the states, and then you've got the state called missing. And it goes just like that. So what you're about to see is a formalization of that idea. So if you suppose that x is a categorical variable with 3 variables and is sometimes missing, you go, all right, well, if x is a categorical variable with 3 values, what does that mean? Well, what that means is there's actually 3 binary variables, but, because the original variable x is sometimes missing, that means that sometimes we don't know what the value of x1, x2, and x3 are, where x1 is the binary variable corresponding to the first value of x, x2 is the binary variable corresponding to the second value, x3 is the binary variable corresponding to the third value. So x being a categorical variable with 3 values and sometimes missing really means that we have these 3 variables which take values 0 and 1 and missing. So we just do what we usually do. We're going to create, for each of these binary variables, we're going to create indicator variables indicating when they're missing. We're going to impute some value to them, like -1. And then, if xk is missing for some k, it appears to us, we go, wait a minute, if xk is missing for some k, well, what that means is that xk is missing for all k, right? Because if x1 was missing and x2 was populated and equal to 1, then you know that x1 is equal to 0. So that wouldn't make any sense. Because x1, x2, and x3 all relate back to a single variable, all of them are missing when the original variable is missing, and none of them are missing when the original variable is populated. And so that's an important observation. And so what that means then is that, yes, you thought you were clever creating these indicator functions here, but in fact they're all identical. They're all either 0 all at the same time or 1 all at the same time. And so what does that mean? It means that when you take those different products of the indicator functions, or 1 minus the indicator functions, all of those products are identically 0 except in 2 cases. This one and this one right here. All right, well, all well and good. Now you make the same argument with a categorical variable that takes n values. And what that means is if it takes n values and sometimes missing, what that means really is that there are n binary variables, x1 through xn, which take values 0, 1, and missing. So again, you go through the same process. You go, all right, well, let's create the indicators for where they're missing. Let's impute the missing values of x with a dummy value, say, the minimum -1. So in that case, just -1. We have the same observation. We go, if xk is missing for some k, it's missing for all k. That means all of the indicators are identical, and therefore only these 2 products of indicators will ever not be identically 0. Good to know. So, how does that help us? Well, what that means is that, among other things, we can show that, in fact, 1 minus the product of all the indicators is equal to the product of 1 minus the indicators. So that's good to know. And so what that means then is that we can create these variables here, and that will be the totality of what we actually need. And then we have another aha moment. We go, wait a minute. In this particular case, the imputed value doesn't matter and may be taken to be 0. And then, moreover, we realize, well, wait a minute. That means that if we take the imputed value to be 0, that means that each one of these guys here, x1 times 1 minus I, that just equals xk for all k. So including this additional factor here in the term, that's not helping us at all. And then because this is really just a bunch of xk's and xi, and we know that xi, or I rather, equals 1 precisely when everything's missing, but when everything's missing, all these guys are 0. What that means is that the sum of these guys is identically 1. So what does that mean? Well, we've got we have n plus 1 binary variables whose sum is always 1. So what does that mean? It means that really we just got a categorical variable with n plus 1 values, and it's always populated. And so in the case that you're dealing with a categorical variable, the simplification is very straightforward. You just treat missing like the n plus first category, and then you move on with your life. So, what did we learn? Well, what we learned was that, in fact, there is a canonical mechanism to handle missing data. We don't have to wring our hands and go, well, this author says this, and this guy said that, and you know, this my professor said this, and in some cases it's good to do that and this. It's like, no. We don't have to go through all that. We can simply go, there is a canonical way to handle this stuff. You do not have to resort to complicated imputation methods. All you need are dummy values and products of missing indicators, and you're in business. And moreover, categorical variables may be considered populated simply by treating missing values as a legitimate value. I hope you found this video useful. Please place any questions in the comments.